you shift that line to the point where you are looking at the derivative, right?
Yes.
All right. So that is a linear subspace in R2, right? Now that can be that you can think of it as image of real line under a linear transformation.
So could you please repeat the statement?
Well, this particular line as passing through origin, you can think of it as graph of a linear transformation from R to R,
Yes, sir. Yes, sir. Yes,
right?
sir. We can think of it like that.
Yeah. So how do you think of that way? So what would be the exact linear transformation? Can you tell me?
Uh, it depends, but I think we can either shift the x-axis to that line and y-axis to 0 and be done with it.
No, no, no. It's
Uh,
not that.
if you could wait, uh,
It is just linear transformation x goes to f prime a x. At a point A you are looking at, then it is x goes to f prime a times x. This
uh,
is the linear transformation.
yes, sir. Okay. Yes, sir.
Right. This you shift towards f of a. So if you look at f of a plus f prime x, f prime, let's say a times x, so this should be your tangent line,
Yes, sir.
right? So so not this, but the graph of it is a tangent line.
Yes, sir.
So we should be looking at the same thing. So you need to think what would that x goes to f prime a times x, this linear transformation. So this is a matrix again, right?
Yes, sir.
But this is a one by one matrix.
Hmm.
So a one by one matrix, so it's a number. So you did not look at as a in the form of a matrix. Now how
Yes,
does
but
this
it can be treated as a matrix.
true?
Yes.
But when you look at, let's say, R2 to R, then you just don't have this kind of number, right? So there, how do you think? So can anybody tell me how do you think if you look at a function from fxy to xy to fxy, two variable, two variable function, and the analog of what I said in R.
So if it's a linear transformation to from Rm to Rn, then it would be a m cross n matrix. Like we could think of it as an m cross n matrix.
Well, that you know because any linear transformation from Rn to Rm it can be represented as m cross what in m cross n, right? Yeah,
Yeah.
right. M cross n matrix. So this is the property of
Sir,
linear transformation. Yeah, Sayan.
so I couldn't even understand what you told the R to R case. Can you repeat it once again? Like,
Yeah.
yeah.
So so how much did you guess? Yeah, try to say how much did you get it first of all.
No, I think I was lost from the beginning only because like I couldn't understand how you're looking at these functions from R to R. I look at derivatives in R to R in a different sense, so I was lost from the beginning.
Yeah. So could you tell me what sense do you look at in the
I think derivatives in in functions R to R derivatives I have always looked at it as tangents, so slope of tangents or maybe rate of
tangent?
changes. Slope of tangents or rate of changes.
Yeah, slope of tangent of what?
Like the derivative at f dash a is the slope of the tangent at the point x equal to a.
That is true. That is
Yeah.
true. So that means you actually have a tangent, right?
Yeah.
So that is what we were looking at. So the question was, how do you find the tangent? So what is the tangent?
Yes, but when we are looking at functions from R2 to R, then the tangent is kind of a plane, right? We don't even have the notion of tangent, because what does to which does this
Of
tangent make an
course,
angle?
true. So tangent is just tangent that is tangent line, right? So the thing we considered from R to R, it was tangent line. Now it will come as tangent plane.
But
It will be
I'm really
line.
confused about how this tangent line, or like I see it as a tangent plane, let's say, and any line on this plane is a tangent to the surface at that point.
Any
So
line passing through that point is a tangent to that point. Yeah,
yes, so
and line in that plane.
like, there is no one specific tangent like we had in R to R. Now I can't understand how this notion of tangent shifts to a linear transformation. How is this notion of tangent related to the notion of a linear transformation?
That's a very good question. That is what actually one should be trying to understand. So, so what is tangent? Tangent is a subspace. Actually, it's a tangent. If you look at all tangent space, right? It's a subspace. Tangent space is subspace, and then you shift that subspace to the point concern. So suppose you have this kind of surface, and origin is somewhere here. So
Sir, just a
the
moment.
tangent.
Are you drawing some pictures?
Mhm.
Are you
I'm
drawing?
showing
Yeah,
by my
but
hand.
you are not presenting the screen, so I don't see, I can't see the picture.
No, I'm not presenting anything.
Oh,
I,
okay, okay,
I
okay,
do
okay.
you see my picture? Do you see my video?
Oh no, okay, I wasn't looking at your video. Just a moment. No, no. Yeah,
Yeah.
yeah. Now I can say, like, okay, yeah.
So I was trying to just I mean try to model with my hands.
Okay, okay.
So
Now I
suppose
can see your
this,
video.
this is a surface, and suppose origin is somewhere here, and and tangent space is a subspace passing through the origin. But then you look at tangent plane or tangent line, it will be touching here, right? And the notion of tangent is actually depends on the notion of curves on on that surface or whatever these things. So if this were a curve, then tangent will be one line. So it's if this were a curve, something like that, the tangent will be one line, not more than that, right? And if it is surface, the tangent, it's actually collection of all tangents. That is tangent space.
Uh,
Is it
yeah,
clear?
the tangent space is clear, but how do you connect that to the linear transformation?
Oh, well, it should be so. So once it is a subspace, right? So how do you find the subspaces of Rn? Can you tell me? How do you find the subspaces of Rn?
These are just the spans of linear transformations, right?
Oh no, span of linear transformation.
Or the image rather.
That is actually you are going to class of all linear transformations, right? So span of linear transformation is not there.
The
Not
image I
not
meant.
Yeah. So what are subspaces of Rn? Let's say if you fix a dimension. So let's say k-dimensional subspaces of Rn. Or in particular, for example, if you consider, let's look at two-dimensional subspaces in R3. How do you find all such?
Sir, we take two linearly independent vectors and then get their span.
Right. You take two linear independent vector and get such thing. Can you connect it to matrix? Or linear transformation?
Solution of linear equations.
Yeah, so Mukul a little bit more experienced people out here. So do you understand what he says? Anybody? So
Sir,
No, sir, not me.
yeah, so it is solution of linear equations.
Sir, can you, I think, draw or like use the notepad? Then it will be
Okay.
better because I am like losing track of all the things because
Oh well, I mean, this is in the beginning. It will be very easy to lose track. Okay, so I'll write these things. These things are basically how you think of these things, right? How you generalize whatever from R to R. Yeah, I'm going back there to share something, some screen or something.
So if you put the
Yeah.
vectors as the if you put the vectors as the columns of a matrix,
Mm-hmm.
then the image of this map
Mm-hmm.
is your subspace, right?
Yeah. So from where to where the linear transformation is?
We were in R3, right? So
Yeah.
okay, that's a problem.
Like this may not be a mathematical thing, but if you take the three vectors, like you take any three vectors that span R3, that is three bases of R3, and you put these
Mm.
vectors into a 3x3 matrix. Now you
Mm.
take any four elements in that matrix which form a square. Like the diagram is clear to me. I can't say it mathematically. Like you knock out an L shape from it somehow, and you take any four elements from that matrix which form a square. Now the vector that these two elements constitute will give you a subspace of R3, a two-dimensional subspace of R3, I guess.
Oh no, it may not be two-dimensional all the time. It might be one-dimensional, or it might be, yeah, it might be one-dimensional as well.
Achha, okay, it depends on the rank, right?
Yeah, it depends on the rank.
Mm-hmm.
Yeah, so you see now we came to the point. Let me share this. The point is, if I share this, I can't see you who is speaking. Okay. But it is very important that you should be uh, able to understand. So let me try to minimize it a little bit so that I can see you also. Can you see my screen?
Yes, sir. Yes.
Okay. Okay, so this is very important. So unless you everybody understands what is what does the derivative means, I will get into trouble. So there is no point going beyond these things and taking all these theorems and all this stuff unless most of you or everybody understands what is the derivative. So that is what my point is. So today is 30th. So the question was, you had, yeah. So how do you think, do you think of derivative of a function or function or a map? So and of course, when this last time, as we said here, that this peaks corresponds to non-differentiable non-differentiable function, and when there is no peak, we'll see this differentiable. Now we are looking at the derivative actually. So f from R to R. Case 1, in the beginning, we should look at what happens from R to R. And then the way to look at, of course, as we as everybody knows, this is looking at if this is a graph, so this is x comma fx corresponding to x, you have fx. So let's say a is fa or a comma fa, a comma fa, and this is the line passing through a comma fa, touching this curve. So this we actually, whenever we think of derivative in case of functions from R to R, we think of this line, right? Think of this line, slope of this line, but this having this line and slope of this line, both are equivalent, right? So once you know the line, you know the slope. So slope, actually slope, and then of course you know that this must pass through a comma fa, so that determines the whole line. So this is it. So, and what is the equation of this line? Yeah, Monodeep, can you tell me what is the equation of this line? I said few minutes back.
Sir, what is the slope of the, if as the slope, the equation is yes, y of x is equal to f of a plus f prime of a into x. Now y of a minus x minus a.
Mm-hmm.
Sorry,
So y equal to
y is equal to
f of a,
y is
right?
equal to f of a plus x minus a into x minus a into f prime of a.
Right. So a prime into x minus a. Right. So and you expand it in terms of Taylor series expansion and look at the first up to linear terms. Right. That's it.
Yes, sir.
That is actually the tangent line. So Taylor expansion does give us a lot of information. So this is this line. So correspondingly, we should try to find a way to generalize this. Our aim is to generalize the above picture. Right? So we need to generalize this portion. And we need the equation as well. Right? So we can tell this is Taylor's expansion because we know a lot more about functions from R to R. But from R2 to R, we don't know much. We know that derivative means a linear transformation. So let us recall the definition again. So suppose in this special case, suppose f is a function from R2 to R, right? Let's assume differentiable. So what does this mean? Yeah, Aditya, can you tell me? Let's say differentiable, which means differentiable at every point. So you tell me when this f R2 to R is differentiable at a point A.
So, I mean, graphically, we saw last time that if it doesn't have any peaks, we find that it's differentiable.
Oh, this is just to imagine. It's not a definition, right? So you tell me the definition. And you see the surface is not right here, right? It is from R2 to R. So what is the surface? That could have peak or could not have peak.
So I mean, if a linear transformation exists such that f of x comma y, sorry, yeah, x plus h comma y plus h minus f of x comma y upon h minus lambda. I mean, if such and such linear transformation exists,
What is the limit? The limit is very important. So what is the limit? So you said there exists
so limit h tending to 0, f of x plus h comma y plus h minus f of x comma y upon h.
limit h tends to 0, f of a plus h. Let's say a point is just a comma b.
Okay.
So a comma b is an actual. So f of a plus h.
Minus f of a.
Oh well, ab I took not.
Oh, okay. Yeah, a plus h comma b plus h.
Well, not same h. Then h1 and h2 has to be taken.
Hmm.
Right? h1 comma h2. This is h1 b plus h2. Or maybe you can write a1 comma a2. That would make sense. Go nicely with this h1 h2. So this is a1 plus h1, a2 plus h2, right? Minus
Minus f of a1 comma a2.
a1 comma a2, then
Uh, Minus lambda h1 h2.
lambda h1 h2
Yeah, upon I guess mod h1 mod h2.
mod h1 times mod h2.
Uh, Mod h1 comma h2.
Yeah.
Yeah. So and this has to be equal to 0. So if we find such a lambda, then we can say that is differentiable.
So we put a norm here also, right?
Hmm.
But that actually doesn't matter.
Huh.
So if you put norm or if you don't put norm, that limit, both the limit, if one exists, other will exist all the time. All right, so we have this one, right? So the point is you have not mentioned what is the linear transformation from where to where.
It should be from R square to R as well.
Right, from R2 to R. So here the norm part is actually unimportant because you are getting numbers.
Right.
All right. Okay, very good. So now the question is, so what is this linear transformation lambda, right? And you look at this one. What is this? This curve? This curve. So Ananya, can you tell me what is this curve?
Hello, sir.
So what is this curve?
Sir, which curve?
So this
Fx.
yeah. So this point I said fx. Actually, fx is just the distance between. So this is fx. This is fx. This length is fx. So what is this curve?
Why? Why is the equation of the curve?
Why is the
Equation of the curve.
no? This is this what I wrote here. This one.
Yes, sir. F plus f dash a into x minus a.
So this is the equation of line, right? You know already this one.
Okay,
This is
sir.
cool.
Yes, sir.
What is this curve?
Sir, this is
This is the
this is
graph
the
of it.
A.
Graph of it.
Yes, sir. R2.
So what is this? As if you write this as set for, what is this? So if you want, I want to write it in terms of set form. So what is it?
A, fx comma x comma fx.
X comma fx. X is not right. So this set is very important to generalize from what happens in R to what happens in R3 or Rn. So you want to look at this set. So here we want to look at the following set: x comma y comma, or maybe since I write x1 x2, so I just write x1 comma x2 comma f x1 x2. Now where this would lie?
In R3.
In
Right. So this should lie in R3. Right? And f is as this. So this is subset of R3. Right? So this is a subset of R3. And so subsets of R3 can be anything, right? So let's say this. So examples of subsets of R3. So of course, I'm not going into discrete and all this stuff, but let's look at this. Is important to understand that what kind of subspace can be this one. So let's say x, y, z, and suppose like this. Let's say it's kind of spiral. I mean, kind of a shape like not like exactly spiraling, but like this. So can this be a graph of this kind?
So this should be a surface, not a path like thing.
No, but do you know what is surface?
So basically, for one particular value of x and one particular value of y, will have only one corresponding value of z.
Right. So that is a correct way to think of. See, for every point in the plane, xy plane, for every point in the xy plane, so here, for every point in this xy plane, you will be determining a unique point in z, right? Not 2 or 3, an unique point, right? So that means the subset you get, the subset, let me write this one. This is interesting. If x1 comma x2, from this set to, so f is of course from R2 to R to R2. Can you give the map? This set to R2, which is invertible. Bijective map. Can you give a bijective map?
We can take the
Just
identity.
x1 comma x2.
Right. The simple one. It's not identity because identity would go to R3 to R3 only.
Yes, what I meant was like analog of the identity x1 comma x2.
Yeah, this is called projection. This projection. So which means this x comma x1 comma x2 comma f x1 x2 maps to x1 comma x2, right? This is the map. Is it continuous? Yeah, is it continuous? So continuous, then which space you will be looking at? You will be looking at this subset of R3 with the metric coming from R3, right?
So do you mean the projection map from a set to, like, from R3 to R2 is continuous or not?
Well, it leads to
And
that.
that is continuous.
Yeah, it leads to that one only. So this map is a restriction of projection map, right? So this is actually is a map which is the restriction of the projection map x1 x2 x3 goes to x1 comma x2. Now this is a linear transformation, right? X2 restriction. So remember, I wrote here restriction. Restriction to what? Restriction of the projection to the set this x1 x2 comma fx1 x2 in R3 to this. So this might not be a subspace at all. This in general will not be a subspace, but this is a linear transformation from R2 to R3. Sorry, R3 to R2, right? So this is a linear transformation from R3 to R2, right? So we are just restricting this linear transformation on this set. So this should be continuous map. Restriction of a continuous map is a continuous map. Yeah, if you are not convinced, then you prove the restriction of a continuous map is continuous. We are not changing the metric. Metric is whatever is in R3. The same metric is restricted to here. So once metric is not changing, the restriction of a continuous map is continuous. All right, so this is a continuous map. How do you know this is a bijective? Or what will be the inverse? Simple, right? Yeah.
Yeah, just attach f of x1, x2 to the end.
Right. So x1, x2 goes to x1, comma x2, comma f of x1, x2. Right. So now this is pretty simple. So we have to have a subset which is bijective to R2 and continuous also. Inverse is also continuous. So it is a homeomorphism, right? So this set is the image of an is homeomorphic to R2, right? Yeah, Sirsa, Kuldeep, Sriram, can you tell me what is homeomorphism? Yeah, what is homeomorphism?
Hello.
Yeah, you can hear you. So what is a homeomorphism?
Sir, I I don't know.
You don't know? Homeomorphism, I was saying quite some time here. So homeomorphism is a continuous map. Say homeomorphism from, let's say, xd to d1 comp to yd2 to metric space is a continuous bijective map whose inverse.
So did we assume that f was continuous?
Yeah.
Did
Yeah,
we
yeah.
assume f was continuous?
Oh, yeah. That has to be. I mean, f is differentiable, right?
Okay,
So,
okay. Sure.
yeah, so differentiable, it's always continuous. We started from there. So here, so of course, this to be continuity is so continuity of f is necessary for this arguments. So this point, you have a valid point. We started with differentiable, that's why we did not talk about continuity. But without differentiability, continuity is good enough to talk about these things. So a homeomorphism from xd1 to yd2 is a continuous bijective map whose inverse is also continuous. All right. So you get a homeomorphism. So it looks like somehow it should be looking like R2, right? So that's how you think of a surface. For the time being, you think of a surface which is well, actually, surface is not globally homeomorphic to R2. For example, if you look at a sphere, it's not globally homeomorphic to. So if you look at sphere, it's not homeomorphic to R2. Can you give an argument? This is a very simple argument. So this is a digression, but an interesting digression.
Sir, can you repeat the question?
Yeah, I'm writing. So is the sphere, so x1, x2, x3 in R3 such that x square plus y square, x1 square plus x2 square plus x3 square is 1 is homeomorphic to R2. So question is the sphere homeomorphic to R2?
So does it have something to do with the fact that the surface of a sphere is bounded, whereas R2 is not?
True. Yes. Yes. It is. I mean, purely question of metric spaces. It has nothing to do with derivative. But this also you think of a sphere, right? This also you think of a surface, right?
Yes.
Yeah. So surface is little more general than what we considered here. So yeah. So can anybody give a
If you
precise
try to
argument? Why should
project
it be?
the surface of the sphere in R2, then the way projections are done, you have to choose one point and then project it with respect to that point. Like basically,
Sir,
Yeah.
may I continue?
Projection will be bounded, so it cannot be homeomorphic.
Yes, so there
Sir,
will be,
S-
yeah. So there will be one point which has to be projected, like which has to go to. How can I explain? Like if you are trying to project x1 comma x2, like the circle on R, what happens is one point has to go to plus infinity as well as minus infinity. The point from
That's
which
not
you
a
are.
projection.
Hmm?
That's not a projection. That's a different kind of thing. Yeah, you're right. You're looking at the. I mean, almost getting to
so,
actually
so
homeomorphism,
the
but exactly not. Yeah, Sadbab?
so the sphere is compact. R2 is not
Right.
compact, so no
Right.
continuous function can be.
So continuous image of a compact set is compact,
Compact set is compact, so
right? So but R2 is not compact. That's a contradiction. But Sion, you have a very good point. That yeah, you can actually remove one point and you can give a homeomorphism.
Yeah, that's yeah.
So this is an interesting question if you can think of, and this has to do with looking at the maps. So you have seen maps in geography, right, in school. So you will see in maths some portions you can get bigger, some portion you get smaller. So this is somehow a projection, not this projection from sphere to plane. So this is an exercise. This is an interesting exercise. Those who are interested can only do it. So let's say sphere x1, so that there exists a homeomorphism from the sphere x1, x2, x3 such that x1 square plus x2 square plus x3 square equal to 1 minus, let's say, 0, 0, 1 to R2. Okay, so this is quite interesting question actually. If you tried, so if anybody try and after that if you can't do or anything happens, you let me know. So this, of course, I don't want to discuss this here in class, but I'll give some time to discuss that. This is a very interesting question. Okay, so let's digression is over. So from sphere, you cannot have homeomorphic, but still sphere also considered as a surface. So these are special type of surfaces. These are not all surfaces, but these are surfaces. So once f is differentiable, these are actually really the surfaces, smooth surfaces. And the aim is, in general, if you want to show something is a surface, you actually want to show this is locally of this form. So this is very, very important. So some subset of R3, if you want to show this is a surface, then locally you want to show it is of this form, locally. So here, the sphere locally is of this form, not globally. So what locally and globally means, you will see by the end of this course or the next semester. Definitely will see it. Okay, so this is really, we are looking at surfaces. We are not looking at any other things. We are looking at surfaces. So this
so for it to be a surface, do we also require F to be differentiable or just continuity suffices?
Well, surface, one can see that this so as you said, what is a curve, right? Curve is a continuous map, right? Similarly, you say smooth curve. So similarly, one can think the generalization as surfaces and smooth surfaces. So when f is differentiable, you get smooth surfaces. So it will look like there will be no peak, right? So this is, for example, yeah, we had two examples, right? So here, this is a kind of a smooth surface, but here, this is a continuous surface. There can be peak, but this is also a surface. So here, the corresponding function is not differentiable. But in this case, here it is. So these two pictures you can keep in your mind, that when function is differentiable, you don't have any peaks. It's smoothly moving. And when it is just continuous, not differentiable, you have peaks. All right? Does that answer your question?
Yes, sir.
All right. Okay. So now let's go back. So we this is not the thing that we consider. So this is this. So this cannot be a graph. All right. So this cannot be a graph. So we are looking at this surface only. All right. So this is almost time. So do we have a class now?
No, sir. It's
So can I take maybe 5 to 10 minutes?
yes, sir. It's okay for me.
Yeah. So what about other people?
Yes, sir.
Okay. So just I'll take 5 to 7 minutes, not much. So here, let's look at a graph. Oh, by the way, so the reference you should be looking at this point, let me mention that. So are you looking at any books? Anybody?
So I think you told to study from Spivak.
Right. Spivak might be a little difficult for some people. So, and even if you are looking at Spivak, you must look at the following book. This is basic multivariable calculus. There are several examples. There are several exercises. You should be doing exercises, calculus. And I'll be looking at this book as well as Spivak's. Okay. By yeah, so this has a lot of pictures, and Spivak doesn't have much pictures. So you will be interested looking at this one. By Marsden, Tromba, and Weinstein. Yeah, this three, all the three are great mathematicians. So you must look at this book. All right. So this is very nicely written book. Very nicely and easy to understand. And it does not give loosely. It speaks actually rigorously, but by first motivating and then examples, then coming to that theorems. Spivak goes actually take the shortest way to important theorems. Okay, so this x, y, z, or maybe x1, x2, x3, whatever you like. So you look at a point here and there, and you look at the tangent space. Tangent plane. So this is called tangent plane. It's a generalization of tangent line. Right. So this is, yeah, maybe I should look at a point right here. Right. And this function, this set is nothing but this xy comma f of xy in R3. F is from R2 to R. Right. So you want to look at this. This is this. You want to find the plane, right? So what is the equation plane in R3? Suppose the plane is, we assume this plane is not vertical. If I assume the plane is not a vertical one, right? So you want to write this plane also as a graph of something. So you don't want particle. Particle case will be dealt later. Then you have to consider the coordinates other way. And this cannot be then graph if it is vertical. So what will be the equation of this equation of a plane? Yeah, anybody?
X minus a dot v is 0, where v is the normal to the plane and a is some point on the plane.
X minus, say that again, x minus?
X minus a dot v equals 0.
What is x?
X is any point on the plane.
So x means xyz.
Yes, sir.
Minus a, which
A.
is a1, a2, abc, let's say. B, C, right? Yeah.
Yes, sir.
So you write not minus, or you so with dot what?
Dot some vector v, where v represents the direction of the normal on the plane.
That is true. That is a general equation of a plane, right? That is definitely a general equation of a plane. But actually, you can actually also write this form. So instead of z, I will write as this is well x naught, y naught, z naught. So this is the point in here, x naught, y naught, z naught. So this is what it is, times or you, as you said, this is dot, right? So you are looking at inner product, right? Yeah?
Yes, sir.
So that let's look at this the vector as a, b, and this one can be taken as constant, right? So that is So this I can take -1. Well, why I can take -1, that you think of. So this is equal to 0, right? Yeah, Akash?
Yes, sir.
This is 0. So this means a times x minus x naught plus b times y minus y naught. You can put c, doesn't matter. But here what I wanted to see is minus z naught equal to 0. So this implies z equal to z naught plus a times x minus x naught plus b times y minus y naught. You can put c, doesn't matter here, but then it must pass through. Of course, it will pass through ABC. I mean z x naught y naught z naught. But if we look, assume that this is not not vertical one, not a vertical one, then you can actually divide by something and get it -1. So if you multiply by constant here, right? If you multiply by constant here, the whole thing, it does not change, right? Does it change? Because this whole constant will be multiplied by all the equation, all the members here. So since it is equal to 0, that constant goes away. So if there is a c here, what you take minus c as the constant. So that's why you can actually get in this one. So this will be the equation of a plane which passes through here. Now tangent, this plane has to be tangent to the surface, that one. So you need to find. So question is here I gave a exercise which I'll do next time also, that assume let's say this is called this is 1, this is 2. Assume the plane 2 is tangent to the surface 1. Find A and B. All right, we'll do it next time fully. So so we had some question remained. One is, how do you find all the subspaces? We'll come to that next class as well. And other question is this one. This is this will get a subspace, but how do we relate it to a linear transformation? The linear transformation lambda we considered here, right? So these questions remain. The linear transformation lambda, how do you relate to that? So we'll consider this again next time. All right. Okay, see you tomorrow.
So just a small question. Like
Yeah,
A
sure.
and B in the equation in which you wrote like ax minus x naught plus by minus y naught plus, let's say, cz minus z naught. Here ABC
Yeah.
plays the role of direction cosines, if I'm not wrong, or direction ratios, right?
That is true, but that actually direction cosines of what?
Of the point, like the point x
No,
naught y naught z naught.
no. Direction cosines actually of it happens to a line, right?
Yeah.
Direction cosines, direction ratios, these are related to a line.
Mm-hmm.
But you are right.
These
are such for the normal.
Okay, yes, the normal passing through x naught y naught z naught.
For the normal line. Yeah.
So, like instead of like when we were drawing tangents in R to R, we were basically looking at the slopes. Here, instead of slopes, we are looking at directions only.
Yeah. So this A comma B comma C.
Okay. So okay.
Yeah, this part. This part was in one case, this f prime a was f prime a was that constant, or this is what you multiplied this side of the inner product, and now you have this one, and one you can make it to be any constant you want by multiplying with constant. Okay.
Yes, sir.
Okay. Any other question? Okay, then see you tomorrow.